Chapter 13, number 48. A 0.285 kilogram mass is attached to a spring with a force constant of 53.4 newtons per meter. If the mass is displaced 0.18 meters from equilibrium and then released, what is its speed when it is at 0.135 meters from equilibrium? So let's look at this and identify some stuff. All right, that's clearly m. 285 kilograms, and that's clearly K. And then, not as obviously, but we have it in here, we have a thing which is displaced some amount and then released. That's A. 0.185 meters. So what's our picture look like? Well, we've got a spring which is pulled back to this distance and then let go, and of course what it will do is move this way, and it will achieve some new position which we'll call x1, and at that time we'll have some speed which I'll call v1. Of course originally it was at rest when released. This is basically just an energy problem, so we're going to say that the energy at release equals the energy at moment 1. The energy at release is 1/2 Ka square plus 0 kinetic, and the energy at moment 1 is 1/2 Kx1 squared plus the associated kinetic energy. And now we can see that this thing is what we're looking for, which is v1. Alright, so we can just sort of solve, and the first thing we do is probably multiply through by 2 on both sides and get rid of that pesky 2. So I'm left with Ka square equals Kx1 square plus mv1 square, and then maybe subtract off Kx square from both sides, giving us Ka square minus Kx1 square, and left with mv1 square, and then divide by m. I'm also going to factor out the k, so I get k over m, and then we have a square minus x1 square, and over here we're just left with v1 square. So we sort of build ourselves a wall here. Then we can say that v1 is just the square root of all that, square root of k over m times the square root of a square minus x1 square. And I do it this way because a couple of offhanded interesting things. For instance, we know this is related to omega. In fact, it is omega. And then this is some sort of Pythagorean thing, which is kind of interesting. Those don't play any particular role here, but it's kind of neat to see it fall out that way. Now we can just put in values. So we have 53.4 newtons per meter over 0.285 kilograms under the radical, and then we have 0.18 meters squared minus 0.135 meters squared, and they're under their own radical as well, and so we're left with 1.6297 meters per second. We have 3 sig figs everywhere, so this really becomes 1.63 meters per second. And that's it.